Hello and welcome to part 2 of this 3-part video on the Voyager Tricorder version 2. This is a continuation from the last video and I left you with yet another showstopper problem. I still had some final testing to do before I was ready to call this done. This whole time I have been developing and testing my code on the hardware. I was running my tricorder in display mode. This was driving power directly off the USB port. I needed to properly test it on battery power to make sure it was all working correctly, but most importantly to make sure nothing caught fire. Now early on I did do some testing with the power circuits before and it did appear to work. It's actually using the same MT3608 DC to DC boost chip that's on the hobby board I used in the first version of the tricorder, so at the time I had no reason to think it wouldn't work. But on testing here I quickly discovered it simply could not handle the full current draw of the tricorder as it is now, with the stability dropping quickly as the input voltage drops below 4 volts and it being utterly unusable around 3.5 volts. While my power draw is still slightly higher than the old version, I really didn't see this as a problem on paper as it was still within the spec of this boost converter. So I had to put this down to being just a poorly documented cheap Chinese part, and it clearly isn't going to work. Now this is bad. The prop simply will not work without a working boost converter. But luckily all was not lost. Unlike the other two tricorders that were unfixable without causing significant damage to the chassis, the boost circuit portion of the PCB was accessible from the bottom hatch and I would be able to hack in a small board to the available solder pads. For a quick fix I started off googling for some hobby boards and I looked at TI's power design tools for a suitable circuit design that I could fit in here. And I was also given some great advice in the 1-Bit Squared Discord. In the end I had two options, both from TI. The TPS61023 and the TPS61032. I ended up ordering both. Adafruit has a 61023 mini modular board that I could order locally and get quickly. But I also ordered the TPS61032 chip from China, but that would take a couple of weeks at least to turn up. This gave me a couple of options. After about a week and chasing my order, the TPS6023 module turned up and I hacked it into the board and begun testing. At first, things looked promising. The power was stable from 4.2 volts down to about 3.2, but by about 3.12 my microcontroller started to reset and my 5-volt rail was getting significantly noisier. Now I don't want to blame this boost chip for this. Reading its spec I knew this would likely hit its current limit and I think the resetting is actually the chip's current protection kicking in. My last best hope was the TPS61032, as after that I really had no idea what else to try. And after all this work I was so utterly burned out I was just about ready to give up. Luckily, this chip didn't take that long to arrive from China, but there was still a problem. These were just the chips. I still didn't have a PCB for them and none of the other components. I managed to source a few parts locally at some significant cost and got started making the PCB. I designed the PCB in KiCad using the datasheet's example PCB layout as a reference, as I didn't want to take any chances with resistant paths or any strange DC PWM issues. And not so bad, due to a small oversight on my part, by ordering the 32 variant of this chip, I've actually ordered the fixed 5V output version, thus simplifying the design somewhat. Now I was not going to place this single order to JLC PCB for this one mini board, and while I do have a bulk order I want to do coming soon, it wouldn't be ready in time to finish this tricorder and I didn't want to wait, so I decided to try and etch this board myself at home. It has been a while since I last etched my own board, but I have been seeing more etching options using paint and laser cutters. Funnily, a similar method to a project I have lined up and want to get started soon. So I got to work. I got my copper boards prepared, painted and etched away the paint. And it seems to have worked, though my laser cutter could do with its belts being tightened and at this scale, its tolerance limits begin to show. This chip also uses a tiny QFN package that frankly was pushing the limits of the accuracy of my laser. However, while it's not super sharp or perfect, managed to etch off the paint well enough for me to then etch the copper, and with a little help from the scalpel to correct any small errors. I then put on the solder mask, exposed that, and then cleaned up the board and ended up with a decent enough PCB. I then carefully drilled some via holes for heat dissipation, flooded them with solder paste and made sure that they made good contact with the copper on the back side that also acted as a ground plane. I managed to solder the components onto the board without too much effort, even managing a decent enough solder job on this tiny QFN, fully intending to bridge the pads that were all connected anyway to make sure that they all had a good electrical contact. I wired this little board into the tricorder and lo and behold, it worked. It really worked. Using my bench power supply, I tested the voltages all the way down to 2.8 volts and this thing just kept a stable 5 volts throughout. You see, the problem I had before was a mixture of the Subspace DC to DC boost converter and certain harmonics coming from the sound driver, as certain harmonics of the scanning sound would cause higher current draws from the amp. These caused small, barely detectable peaks in the current. These peaks would either drain the 5V rail enough to shut the thing down, or trigger the boost converter's overcurrent protection. But with this boost converter having not only a higher current allowance, it also had a beefier output capacitor that was able to supply for those tiny peaks. So, now it's done? Well, almost. I still needed to make sure the battery draining and charging circuits were working correctly, but now I could safely run my battery with a working boost converter. It was time to test just that, and yeah, it worked. After fully charging a partially charged new flatback battery, I measured the total on runtime with the door open. This is with all the sounds going and LEDs and display running, and the battery lasted 1 hour 40 minutes before the overdrain protection shut it off. While admittedly this is a little shorter than I would have liked, and certainly doesn't remotely match what the Mark 9 would do while the show was in production, lasting a day or more on one set of batteries constantly going, it's unfair to compare the two props, as this is also running sound and an LCD display as well. On the 5V rail, it has an average current draw of 400 to 600 milliamps when turned on. With the door closed, however, it goes down to around 150 milliamps. So I feel this is still fine for cosplay use, not that I really do cosplay these days. One slight downer here though is the recharge time, as it takes around 3 hours and 20 minutes to fully charge. This is a 1200 mAh battery with a charge and discharge rating of 1C. While I'm not using that full 1C charge allowance, I felt keeping my charge rate to around 1 amp rather than 1.2 amps would be both the safest option and also would give the battery the best life. I have also positioned the battery so it can be taken out and replaced when it wears out, or if it was to go the way of some other bad batteries and balloon up. Now, after all this very long explanation of how it all came together, let's take a look at the finished build. Inside the back hatch, you can see 3 switches. The 2 small ones are option switches. The one down to the bottom here switches the sound on or off. This can be used to save battery power or because you have this running in a display. The second switch hacked here behind the hacked in booster board is the charge or display mode switch. In charge mode, the power that comes off the USB charges up the battery. In display mode, the 5V of the USB is fed into the 5V rail of the tricorder, powering it directly. This means you can have this sitting in the display cabinet and turn it on or off via an external switch. This is also how I powered it while I was developing and testing the software. Up here is the main power switch. If the charge or display mode switch is set to display mode, the tricorder will be turned on regardless of this switch, as power is applied through the USB cable. But in charge mode, this switch will turn on the power from the battery, so let's turn it on. Much of the functionality is designed to mimic most of the features of the old tricorder, but with some updated perks thanks to the new hardware. On a fresh start, when I open the tricorder, it shows the startup sequence like the old tricorder, and after that is complete, it goes straight into the first scanning page. Like the old version, this has sound, both the scanning sound and beeps when you touch the buttons. Also, like the old version of the tricorder, all the buttons on this tricorder are capacitive and beep when touched. And the touchscreen is also detected, though in most cases it simply returns a beep as well. This page is a new design and the first UI I designed while testing the new hardware. It's a hybrid of the old Science UI from the Mark IX style that was used in the first prop, but edited to fit within the UI aesthetics I have gone with in this new build. Right away you can see that I have a more dynamic UI. On the previous version, it wouldn't have been possible to run the bar graphs changing positions like this on the next-gen display. The E-chip I'm using allows me to really create a dynamic UI that mostly does what I want. All I have to do is write code that spits out the correct order of OpenGL like vertex commands, and when ordered to render those commands, the chip does its thing. Of course, I'm somewhat oversimplifying that a little, but this new direct rendering approach really gives me a lot of power to make great dynamic UIs. Like on the old version, long pressing the sensors button loads the next page. The next scanning mode is a new take on what I called the wideband scanning mode, another generic science graphic, an updated one I had from the old tricorder. Again, this chip giving me more freedom to add a level of dynamic rendering that just was not possible on the next-gen display, such as laying this targeting graphic over the sciencey blob. Loading the next page, we have a new updated medical scan page. Also like before, all the LED sequences change on each scanning mode. The medical scan showing a similar LED pattern on the front scanner as seen in the next generation medical tricorder when Beverly removes the front scanner. Again, the new graphics hardware allows me to show a more detailed scan over the humanoid figure, showing various internal details. Again, this was simply impossible to do on the next-gen display. Changing the page again, we see one downside to the new hardware. Not so much a fault with the display chip itself, but more the method of passing the asset data into RAM. This UI uses nearly all the available 1MB of asset RAM space of the chip, and so it's not an instant load. 1 meg may not seem like a lot, but with the assets being stored on a slow SD card running in SPI mode, the speed is limited, so it takes roughly 2 to 3 seconds to load this page. Having the assets stored in a faster flash chip of some description might be one workaround for this, but for now I felt this issue wasn't big enough to warrant another design change. In this UI, the asset that took most of the size was in fact the large map graphic I used. Having this large graphic allowed me to give it a panning effect as the tricorder scanned and focused on areas of interest. This is one of the UIs that took a fair bit of time to program as I had to write each stage of the sequence. This UI was a pain to do, but I feel the end result justified all the effort. The next UI is a metallurgical scan. This is a somewhat simpler looking scanning page, but if you look at the stack of numbers on the right, this also proved to be a good challenge. Aiming to look like the effect on Voyager where stacks of numbers seem to be organised and randomly selected, I wanted to copy this effect. Again, all the numbers and selected lines are random and run within their own sequence. It's a cool effect that looks deceptively simple, but this effect did take about a week or two to figure out and debug. But again, it's one I rather like and I'm happy with. The next UI is an updated version of the same power-filled UI from the old tricorder, thankfully one of the more simple and fastest to write UI pages. The next UI is a heavily updated Subspace scan page. In the old version, the wavy Subspace frequency line was a static image and some simple bar graphs rendered over it. In this version, I have gone with creating a function that would draw these graphs dynamically. Again, this is something simply not possible to do in the next gen. These now regularly change their shape in a random way. This UI did also pose a possible issue with the Eve chip, but it turned out to be fine in this instance. The graphics chip has a hard command draw limit of 2048 commands. Now that might seem like a lot, but to draw a single bitmap graphic takes around 5 or 6 commands. To get these wavy lines, I had to draw multiple layers of lines, not only to fill in the wavy subspace bar, but also to add a border line to this wavy effect. These essentially are vertex point commands. And like polygons, I needed to add a lot of interpolated points between main key points to give a graph a smooth flow. I had to find the right balance between having a rough and smooth edge while keeping the command list down, as each extra interpolated subdivision could add 100 or so extra commands to be sent, which would mean I could quickly run out of available command space and crash the graphics chip. Luckily, I was able to find the right balance when making this UI, but the limit was a concern when I started it. The final scan UI is the molecular scan UI. Again, a somewhat simple UI scanning a string of molecules. Pressing the sensors button again brings us back to the beginning, and you can keep pressing the sensors button to constantly cycle through each UI. The final effect I want to show you is the emergency function. Pressing the big red button starts the sequence. And long pressing the emergency button starts the countdown sequence. If I press abort, it will return to the previous scanning page. This time I will press the emergency button again and let the countdown complete. The tricorder now goes into sleep mode. Well, I say sleep mode. The only way to take this out of the state is to long press the power button, which brings you back to the fair scanning mode. One other small update to this build is the inclusion of the door closing hall sensor, which allows the tricorder to start the door closing ratchet sound around the time you start closing the door, rather than once the door is already closed like on the old version. This is a new simple addition I rather liked. So that's about it for this video and for this build. So what's next for the tricorder? Well, in this build, one major fix I had to hack into it was the new boost converter. This change will now be reflected in the new PCB design. And this build is still far too complex for me to make many more of, so some changes are already being implemented in the design. Even as far back as a couple of months ago, I had already begun working on the new PCB design that is aimed at simplifying the building process. Not only is this PCB easier to put together, it's also designed to make it easier to take the tricorder apart to make repairs to the circuit if need be. Some other changes will also include the main faces of the chassis being printed along with the tricorder body, as well as some internal mounting points for PCBs to be mounted to. I will also be slightly tweaking the hinge design yet again, to fit the hinge hoop strips into slots within the chassis and have them bolted in directly. This to further improve the strength of the hinges. There may also be some cosmetic changes as well, as I may now remove the deep recessed buttons and make them more level, again with the aim of simplifying the build but also to improve the lifespans of the decals themselves. Like I say, this project has seriously burned me out. It's been going on for far too long and it's been a bit of a detriment to other projects I want to do as they've all been put on hold. But it also means I've not been able to release as many videos on this channel as I've wanted to. This actually is detrimental to the growth of my channel on YouTube as well, as it makes the ever elusive minimum watch hours per year to get monetized here even harder to reach. Now, I don't run this YouTube channel with the aim to make real money. I know that's never going to happen. I use this channel to show off my projects. But I would like to be able to get to the point where I will get some income off YouTube so I can offset the costs of my projects, as they have not been cheap for me to do. But in the meantime, I have a Patreon page where you can help support me and the projects I build on this channel. Along with this new video, I am now announcing the new super support tier for the channel with some added perks. In this new support tier, you will now get access to some of my designs and future projects. While the tricorder itself won't be made available, I have already placed the KiCad project file for the display development board I showed earlier in this video into the list, as well as a couple of other works in progress for projects I will be working on in the coming months. This tier is still early days, but I plan to add more and more projects to be made available as time goes on. If you wish to support me and the work I do, please consider becoming a Patreon member, or if you like, you can place a one-off GoFundMe donation. All the links are in the description. In part 3, I will be going into more detail on some of the software and the hardware development. This will include a walkthrough of how the program is organised and some of the program's flow. I plan to have this video out in the next week or so. Thank you for watching. I hope you enjoyed this video. This project really has been a massive pain, but in the end I hope the effort has been worth it and you have taken something away from it. See you in the next one. Be safe, take care, and goodbye.